focus to actuators. So the first 8 lectures were devoted to power electronics, the first part of the course, which will allow us to control motors and actuators later. So today you're going to start the fundamentals of electromechanical energy conversion, and this is the foundation for all the electric machines that are going to see from here on. So this part of the course tends to be easier than the first part. We have 2 courses. The reality is you have 2 courses in one. You have to fit a lot of contents in one. So this second part is relatively easier compared to the first one. And the concepts you're going to see here is basically how different motors work and what we need to build and model them. So today we're going to start with something relatively simple, the fundamentals of electromechanical energy conversion, how we go from electrical energy through field energy to create mechanical energy. This is the principle of operation of most electromechanical actuators. The coupling between the electrical and the mechanical side is the magnetic field that is generated from the electrical side. We're going to see today how they are related and how we can estimate roughly what force a solenoid, for example, can exert on a moving part based on the coupling between the magnetic and the electrical, the magnetic, and the mechanical energy. So for this lecture, we're going to calculate the stored energy in the electromagnetic system, understand the principles of energy conversion from, again, electrical to magnetic to mechanical energy, and model and analyze an electromagnet. As I said, the most important application of what you're going to see here is electric machines. Here is one example of an electric machine. This is a DC motor. The DC motor converts electrical into mechanical energy and vice versa. And the question that we can ask here is, how is that happening? What is the coupling between the mechanical and the electrical side? It's the field energy, is the magnetic energy, and how is that conversion happening? We see here that we have coils that will receive power from the electrical source, that will generate a magnetic field that stores magnetic energy and eventually creates a force acting on the mechanical part, and the system moves. So how is all that happening? Today you're going to limit ourselves to the energy conversion part. You're going to see DC motors precisely in one of the future lectures. Another application is this Maglev train. You have probably heard of this. This is a prototype, or is this the one in China? I believe this one is the one in China that connects the airport to downtown and in the capital. And this train will operate based on the principle of magnets that lie on the track, and you have coils on the train that are used to levitate the train and propulse the train. How is that happening? Is the principle here would be the principle of operation of induction motors or synchronous motors, something you're also going to cover later. Electromagnets and solenoids are used in mechatronic systems for a variety of reasons. The picture is not showing here, but it's showing in your copy. How can you model this actuator and estimate the force being deployed by these kind of actuators? Some of you are working on designing a dual engine or multi solenoid engine. So how can we estimate how much force the solenoids can deliver, and what is the power they take? What are their maximum speed, displacement, and so on? Something that we are also slowly going to build up to and be able to model in the next lecture or the lecture after that. All right, for the energy conversion process in electromechanical systems, we have 3 main parts. The first part is the electrical system itself. That's where the power comes from. We have a power input that we call here PE, the electrical power to the system. That power is delivered, it creates a magnetic field. That magnetic field now stores energy in the form of magnetic field, in the same way that the electrical system stores energy in the form of it stores electric energy. And the magnetic field then generates a force or a torque that is delivered to the mechanical system, which in turn also stores energy. And the output of that system is the mechanical power delivered to whatever we are actuating with that actuator. And this process, of course, this process is not 100% efficient. There are several losses in the way. The first one occurs in the electrical system itself. The most common one, or the principal one here, would be the Joule losses. If you apply a voltage and a current to a winding, the winding has a resistance, and energy is dissipated in the form of heat, and that is given by the current squared times the resistance of that winding. Once we pass the electrical loss, then the net amount of power, that is PE minus Joule losses, I squared times R, is delivered to the magnetic field, the coupling. And there we also have some energy losses. What are the energy losses in a magnetic field, if you remember from transformers? Where can we dissipate the energy in a magnetic?
The eddy currents and having to actually magnetize the core.
Exactly. So the magnetization of the core is not necessarily an energy lost. We are not dissipating energy there. It's just an energy required to magnetize the core. But indeed, the eddy currents are another source of energy that is dissipated in the form of heat. So if you are dealing with an alternating magnetic field, we know that in a closed path in a conductor, that it will create currents looping at a high frequency, at the same frequency as the input. And those currents then create heat and dissipate energy. So the field loss here mostly corresponds to eddy current. And then eventually we have the mechanical system. And for a mechanical system, like any other, energy is dissipated again in the form of heat, but this time through friction. Any friction between moving parts dissipates energy in the form of heat. So all these losses are dissipated in the form of heat. We can now add all these energies and create a balance of energy. So the input to our system is the electrical energy, which corresponds to the sum of the mechanical plus the field stored energy. Field stored energy, by that I mean the magnetic energy stored in the system. We are going to refer to that as field energy, and the energy loss. Right? And again, if you look at the summary here of all energy losses, we have Joule losses for the electrical system, friction for the mechanical system, and eddy currents for the coupling field. All these will actually dissipate energy in the form of heat. Here we have two examples of possible actuators that we can build in this principle. The first one is a speaker. The speaker receives an electrical impulse. The impulse is converted into vibrations through a magnetic coupling. The second one is a stepper motor, which works on the same principle. We have coils, we have a ferromagnetic path, we actuate the coils, and the coils exert a force on the rotor rotates, and that rotation is then the mechanical energy that is converted from the input to the output. And there are many more. All right, so if we have our balance of energies, input energy equals to all energy plus losses, we can also say that the same holds for a instantaneous energy change, that is the power basically. The instantaneous energy change, or the time derivative, of the energy also holds. We can take the derivative of the first equation, so a small change in the electrical energy results in a small change in all other energies in the system. If we now neglect the energy losses, we are left with three terms only. The variation in the electrical energy equals to variations in the mechanical energy and the field energy. So let's consider this solenoid that we have here. This is an electromechanical actuator. We have simply a coil around around a ferromagnetic path. This creates a magnetic field once we apply a voltage to it, a current, I should say. This magnetic field now eventually creates a force that will attract that moving plate towards the core. And once we we stop the energy input to these solenoid, then the plate goes back. So here we have the electrical part. That's a solenoid that is modeled as a RL system. We have the field itself, the ferromagnetic path that stores energy there. And you have the mechanical moving part that also has its own energy. Let's assume that in this system, we now apply a voltage V to this this actuator, and this voltage V has a current flowing through. The current establishes a magnetic field, so there is field energy. But let's assume that the system does not move. If the system does not move, then G is constant, which means that its own derivative is 0. If that is the case, then the mechanical part has no energy. The energy in the mechanical part is also 0, under the assumption that it doesn't move, of course. If it doesn't move, the mechanical energy is 0, which means that we can now equate all energy given to the system in the form of electrical energy to the stored energy in the form of magnetic field. Again, assuming no losses, all electrical energy is delivered, is transformed into mechanical energy. Sorry, into field energy. All electrical energy goes into field energy. The electrical energy is easy. We know that the energy is the current, the integral of the current times the voltage over time, basically is the integral of the power over time. And if you're dealing with a small change, the derivative of that, then we can simply do the derivative of the electrical energy equals to E, the voltage, times I, the current, dt. Now, if you take the integral of that, we go back to the integral of the power. So for the energy, the electrical energy, that is easy, nothing new here. What is the field energy? Well, what is the magnetic energy stored in the core? That's the question we're going to answer next. Right? From equation 4, I don't think there's anything new here. Considering again the same solenoid that we have, in the same way we defined the electric energy as I E dt. I remains the same, but now our variation in the current in the voltage is simply d phi, and if you d lambda, and you remember lambda is, this is the flux linkage that we defined as the magnetic flux itself times the number of turns in a coil. So this alludes to the EMF, some sort, induced in the core, because these are, here we are dealing with the derivative and a small change in the flux linkage. We can take the derivative of that, and d phi d lambda dt equals to n d phi dt. All right, and what is this? This is exactly the induced EMF, isn't it, from lecture 2? All right, so d phi, sorry, I keep saying phi, d lambda dt is simply the EMF induced in the core through changes in the magnetic field. If you now take the integral of that, that is simply the integral, the energy is stored in the form of magnetic field. Right? So we can make an analogy with the electrical part where we have I times the voltage. Here we have I times the EMF, and the EMF is the variation of the magnetic flux over time, the derivative of the magnetic flux over time times the number of turns in the coil. And that is equivalent, as the equation here shows, the equivalent to d lambda, the derivative of the flux linkage. Now, if you want to find the energy itself, simply take the integral of that from 0 to lambda, I d lambda. And again, lambda is the flux linkage, which we just defined. And in this way, now we have an expression for the magnetic energy stored in the core. And you can see that we can make an analogy again with the electrical energy. Any questions so far? No? Okay. So some of these concepts we covered in the last lecture, not in the last lecture, in lecture 2. All right, so now let's take this approach one step further. We know that the field energy is, as we define here, integral of I d lambda. Now let's define I, and let's define lambda. Let's define the current, and let's define the flux linkage as a function of the magnetic properties of this solenoid or this actuator. The electromotive force relates the magnetic field and the current. We remember that equation, integral of a closed path of HDL equals to Ni from lecture 2. Right? In this case here, if you take this integration, we have H for both the core, and you have the length of the core, and we have the magnetic field in the air gap times the length of the air gap. And this is equals to number of turns of the coil times the current. So from this, we can obtain an expression for the current. Here it is. Nothing new here once again. And now we take this expression for the current, and you can move that or replace that into the equation for the field energy here. And this is what you get in equation 9. So this whole part here is the current I. Okay, where again, L is the length of the magnetic path for the core and for the air gap. And H is the magnetic field intensity for the core and for the air gap. Okay, now that we have done that, we still have here the lambda to define. So let's work on that one now. In order to understand what the flux linkage is, we first need to go back and redefine the magnetic flux itself. We know that the magnetic flux is defined as the magnetic flux density, B, times the cross-sectional area. So B is a density. If we multiply that by the area, we get the magnetic flux. This is once again from lecture 2. And for a coil with n turns and no flux leakage, the flux linkage can be defined as simply the multiplication of the number of turns in the coil times the magnetic flux, which now can be related with Faraday's law from this equation. So we can replace, we know that phi equals to B times A, and you can simply replace B times A there, and here is what we get. So the magnetic flux linkage equals to the number of turns times BA, and BA is the magnetic flux phi. If you now take the derivative of that, a small change in the magnetic flux linkage, it will likely occur from changes in the magnetic flux density. Not on the number of turns, those are constant, not on the solenoid area, that is also constant. The only change in the magnetic flux leakage must come from changes in the magnetic flux density. And that's why now if you take the derivative of lambda, that is NIdB. Only B is changing, everything else is constant. With that, we go back to our original equation. Remember that here we had d lambda and simply replace the new definition for the magnetic flux linkage. And now finally we can integrate this. Okay, we can now integrate because you see that we have dB and we have H. We have the flux density and the magnetic field intensity. For the magnetic flux density, we know that that is phi over A. And we know that the relation between them and H is mu times H. Right. So for the air gap, mu is likely to be, it will always be constant. That's the permeability of the vacuum, and that is constant. So if that is constant, we can assume that the magnetic flux density in the air, not the magnetic flux density, we can assume that the permeability is constant, so we can do the integral on the air gap. However, for the magnetic core part, the permeability is not necessarily constant, because after a certain value, that value decreases and we see some saturation. The magnetic core will not develop the same magnetic field for a very high value of the field. The magnetic core will not develop a very high flux density for a certain amount of the magnetic field, because the relation now becomes non-linear and the core saturates. So that if that relation is not linear anymore, it will depend on the intensity of H, and hence the integral cannot be solved. We have to be left in its generic form. However, for the air gap, that doesn't apply. It's always a constant permeability. So that side of the integral can be expanded and solved. Very well. So here we have two parts now to deal with. We have N here will cancel out, and we have the core, and we have the air gap. If we assume, once again, the cross-section is constant for both the air gap and for the core, then we can say that the magnetic field intensity and the magnetic flux density in the air gap can be related like that. So B is the same throughout the entire magnetic core, which allows us to now split equation 12 into two. So we take the first part of the equation, that's the core, and we can integrate that. So core times core field times the core path times its cross section. Integral of that dB is the first term of the equation, and the second term of the equation will come from this part here, where we replaced H with B over mu. So this is the same equation now rewritten for each part, for the core and for the air gap. What do we see here? We see that for the core, we have the field times A, its cross-section, times LC, integral over dB. And for the air gap, we have B over mu, again, under the assumption that mu0 is constant. That's why we can do now the integral there, times A, the cross-section, times its core. What is A times the core length? Isn't this the volume of the core? And what is A times Lg? This is the volume of the air gap. So now the energy is stored in the core and in the air gap will depend on the volume of the air gap, with the volume of the core, and also on the intensity of the magnetic field that is established in each of them. Okay? Any questions here?
Yeah, what was our bounds of integration for this case?
Sorry, could you repeat that?
What is our bounds of integration?
The bounds would be from 0 to B, because you're integrating over dB.
Okay, okay.
0 to B.
And that's the B that you said was constant throughout the whole core and the air gap?
Exactly, that's exactly it. Otherwise, this relation would not hold, and it would need to write H air gap.
Right.
Okay. We can only replace that with B over mu, assuming that a B in the core and B in the air gap are the same.
Gotcha. Okay, thank you.
Which are, they are, assuming that the cross-sectional area is the same. All right, so now the field energy depends on the intensity of the magnetic field and depends on the volume of each part. So now we can continue. So if you call this volume for the core Vc, we are left with integral of H dB times Vc. That's the energy stored in the core, plus, now the integral here is relatively easy to calculate. That is B squared over 2 mu0 times A Lg, and this is VG, the gap. All right. And you see here that the integral was left in a generic form because mu may not be constant, whereas here mu is that of the air gap and it is constant, so we can solve the integral. Okay, so now we can do some definitions here. This first term, if this is entire energy and this is the volume of the core, we can say that the integration part that is in parentheses here is the energy density in the core. This is the energy density in the core, and this is the volume of the core. So when you multiply them, we get the energy in the core. This term is the energy density in the air gap, and this term is the volume of the air gap. When you multiply them, we get the energy in the air gap. Right? What is the unit for the energy density? That would be joule per cubic meter. And what is the energy? So volume is cubic meter, so that time one times the other, we have energy as joules. Okay. So here are all the definitions. And typically, if we design our system correctly, the permeability of the core will be much greater than that of the air gap. So most of the energy will actually be stored in the air gap. Most of the energy is given to the air gap because it takes much more energy to magnetize the air gap than it takes to magnetize the core, assuming that the core permeability is greater than the air gap. So most of the energy will be there, which means that we can assume that the field energy for most applications is approximately the field energy in the air gap. Right. So if we now want to calculate the force is developed in this process from the field to the mechanical energy, we'll end up having to determine how much field energy we have. We'll take the derivative of that, and any changes in the field energy will go to the mechanical energy. We now have to define the principles of energy and co-energy. We saw that the field energy was defined as the integral of I, the lambda, the integral of I times the derivative of the flux density from 0 to the flux density itself. If we now plot these as a 2D graph, that's what we get. Lambda and I. Remember that a lambda here is n phi. So we apply a current, we establish a magnetic flux times the number of turns. This integral simply represents the area under this curve. If you're doing d phi, integral of I d phi, then the area is here on top of it. And you can also define what you call the co-energy. We just flip the equation around. We now do the integral of lambda di. We'll take the other side of the integral. Take the other side of the curve. So one side is the energy, the other side is the co-energy. What is co-energy? Co-energy doesn't mean anything physically. Co-energy is just a mathematical shortcut they're going to use later, because in some instances, this motion in the mechanical part will generate a constant magnetic flux linkage or a constant current during motion. So the co-energy is just a shortcut that we can use to simplify the integration to find the energy later. But in reality, it doesn't really mean anything. If you are taking both sides of this curve here and you have a linear system, this means that this relation between the established magnetic field and the current required to establish that magnetic field is linear. And if that is linear, then both sides of that area will be the same. Energy and co-energy will be exactly the same. This area equals to this area. However, some magnetic materials are subjected, or most of them are subjected to saturation. So after a certain amount of current, this linear relationship no longer holds and the system starts to saturate. Only in those contexts, then energy and co-energy are not the same. But for the purpose of our analysis, we're always dealing with the linear range. Energy and co-energy will always be the same. So once again, energy in the field is what we just calculated. Co-energy doesn't carry any specific physical meaning other than just being a mathematical shortcut to do that integral in a scenario where either the current remains constant during mechanical motion or the magnetic flux linkage remains constant. So now let's study that in more detail. Let's consider the same solenoid that we had before, the same actuator we had before. Now let's assume that once we apply the voltage to this, the plate moves. It moves from G1 to G2. You see that the gap decreased, so the plate is closer to the core. There are two possible scenarios here if you look at the same I lambda graph. The first one is where the motion occurs slowly or the motion occurs quickly. So if motion occurs quickly, let's look at that. The motion occurs quickly. What happens to the current? So for a constant voltage during motion, what happens to the current? Any guesses? Should the current remain constant or should the current change? The current will have to change. If motion occurs fast, then the plate moves towards the magnetic core fast, the current changes. Why does the current change? Why does the current change?
Is it the decrease in volume of the air gap?
It is a decrease in volume in the air gap, yes, but this decrease will only occur during motion. Once the plate stops and reaches zero speed, the current goes back to its nominal current. So if you apply, let's say, 12 volts here and you have 1 amp going in, if you move the plate back and forth, during motion, that current changes. But when the plate stops, the current goes back to 1 amp. Why does it change when the plate moves? Moves fast. Because the magnetic field inside the core is changing. By moving the plate, we are changing the reluctance of the air gap. Remember that the reluctance of the air gap is L over mu A. L is changing. We are changing the resistance to establish a magnetic field. If you go farther from the plate, there is more reluctance, the magnetic field decreases. If you go very close, that reluctance decreases, and hence the total magnetic flux increases. Hence, as the plate moves, and if it moves fast, there is a change in the magnetic flux. The change in the magnetic flux creates a back EMF in the coil, and that back EMF in the coil decreases the current, or increases if you go the other way. And only happens during variations of the magnetic field, variations of the magnetic flux. That's why once we stop moving, the current goes back to its nominal current. And as it moves, and it moves fast, then the magnetic field is changing. So we have an induced EMF in this form because the flux is changing, and then the current, of course, will change. That's scenario one. Now, in the second scenario, the plate moves slowly. If the plate moves slowly, then you can assume that this tends to zero. And what changes? Then the flux linkage changes during that motion. The flux linkage will have to change during that motion, and the current remains constant. Okay, so these are the two possible scenarios to consider. Any questions here? Is it clear why the current, this is a good midterm question actually. Is it clear why the current changes when motion occurs fast? Yeah?
Question.
Yes, go ahead.
So I see sort of why the current changes when the motion is fast, but it would change when the motion is slow too, right?
Yes, it would, but we are assuming to simplify the calculations later that it changes, but it's insignificant, it's negligible. And if it's very small, then d phi dt, phi changes, but if d phi dt doesn't, or not enough, to create a change in the current. But you are right, mathematically, this is an assumption because mathematically it has to change so long as there is motion, right? So long as the speed is non-zero, yeah. But if it's small enough, then we can make the assumption that if the current now remains constant, then something else needs to change in this lambda I curve, and that will be the flux linkage. Right? So that
Okay,
would be
thank you.
the second scenario. Very well. So those, there are no questions. I'll add that to a hypothetical midterm. All right, so let's do case one. The movement of the plate occurs quickly. The current changes, the current drops. And once again, this is only valid during motion. Once we stop the plate, the current goes back to what it was. I had a demo last year in class. This year, unfortunately, I cannot show it to you. And now we can say that this change in field energy will be delivered to the mechanical energy. So any change in field energy results in changes in the mechanical energy. What is a change in the mechanical energy? That is simply the force times displacement. Force times displacement is the work of power, right? Is the work. If we integrate that, we get the energy. And we can equate now that to the field energy. If you want to solve for the force, now we have the mechanical force equals to the time derivative of the energy with respect to the displacement. Notice here that we used the field energy equation. We use the field energy equation because we assume that if now the current changes, if the current changes, then the field energy remains constant, the flux linkage remains constant. And if the flux linkage remains constant, it is easier to take the one of these integrals where the flux is constant. Right? It makes our job a lot easier. So we'll take the field energy equation. If we go with the other case where now the movement occurs slowly, then the current remains the same and the flux linkage now changes. So you can say that now we observed a decrease in the field co-energy instead of energy. And you then use the other equation because now we have a constant flux linkage. So it is easier to take the integral for a constant flux linkage. Both equations are equivalent. We see now that the changes in the field, the mechanical energy equals changes in the field energy. We are using the co-energy, but again, energy and co-energy are the same for a linear system. So this equation is similar to the other one, except that now when you calculate the co-energy, we will take the integral for a constant current as opposed to a constant flux linkage in the case one. And we can now calculate simply the mechanical force by taking the time derivative of the co-energy with respect to the displacement of the plate. And this holds for a constant current. Okay, so this forces, if you calculate one way or another, it should give us the exact same result, provided that the system is linear. Okay, any questions?
What is CTE? Maybe I missed that.
Constant.
Okay.
I is constant. That's what it means. Any other questions? You'll see there's a lot of integrations and derivations here, but the application, this is relatively simple. No? All right. So let me try to, we had an experiment in class last year. Unfortunately, this year we can't do it. But let me try to explain that to you. So let's now look at the effects of hysteresis. If we have a, let's say, this actuator like that, we can apply a voltage to the solenoid. The voltage creates a current. The current creates a magnetic field. The magnetic field now creates a mechanical force that eventually attracts the plate towards the core, and they touch each other. So if we start to magnetize our system with a current, I'll put the current here along the input to the system, the magnetic field. And that magnetic field now creates a magnetic field density in the core. So if you start to increase the current, we should see an increase in the magnetic field up to a certain point that is linear. The magnetic field density eventually saturates. And now we start to see a nonlinear curve, the permeability changes. Now let's decrease the magnetic the current, and let's see what happens to the magnetic field density. Ideally, you would just go back following the same curve. But the problem is that it will take a different path. You will actually go like that. And we'll reach a point here at this specific point where the current is now zero, the input is zero, but there is a magnetization in the core that is non-zero. What is happening here? This is the effect of hysteresis. When you have a ferromagnetic material and we apply a current to it, we create the magnetic flux density, and the dipoles of each element, each particle in the core will now align itself with that magnetic flux density. And once we remove the magnetic field, the external magnetic field, they remain aligned. They remain all aligned in the same direction. And they maintain some sort of magnetization. This now behaves as a permanent magnet to some extent. Of course, a weak permanent magnet. The output, the input power is zero now. There is no current being delivered, and yet there is a magnetic flux established in the core. So that's the effect of hysteresis, which means that in this plate here, if we, let's say we take this magnet to lift something, we connect them, we apply a force, apply a current, so there's a force between them, and you turn off the current, the plate remains attached to the core, and you'll take some force to let it go, to detach it. And this is due to the effect of hysteresis. Now we can continue this. Yes, go ahead.
So are you saying basically once you apply the current, it magnetizes the core, and then when you take the current away for a short period of time, that core is still magnetized and can still like attach metals, I guess?
Yes, it's still, yes, exactly. And it's still, so it behaves like a permanent magnet. Of course, with a weaker magnetic field that we would have at the peak here. I'm exaggerating this on the graph, but it would have what we call a remnant magnetic field when the current is now zero. And now we can continue this. We can continue to decrease the current, and we'll reach a point here where now we have the opposite problem. The current is non-zero, is negative, but the magnetization in the core is zero. And you can keep going and then back. Now increase the current, and you reach the opposite point there, where now we have again a current that is zero, yeah, and the magnetic flux in the core that is not zero. And you keep going like that. And this is the magnetic hysteresis curve. It depends on the direction of the core, of the current. And we always have what you call the remnant magnetic field, which poses an important problem, because here current is non-zero, magnetic field is zero. Here again, current is zero, the magnetic field is non-zero. All right, this is a real problem because it makes everything nonlinear. How do we get rid of this remnant magnetic field? Let's say we are here, we are at this point there. We apply the current, we remove the current, and the thing remained magnetized. How do we remove that magnetization? Well, we can simply apply a reverse magnetic field and bring it to that point, and then turn off the current. Or we can apply a very high temperature to the magnetic field. That's called the Curie temperature. And when you reach a certain threshold, it demagnetizes the material. Right? Or we can have some sort of current that it has, if you're a project, this is the easiest way. Just have a current over time that it decreases like that, and just brings this small path here like that, slowly to 0, right? By applying a current in that form. Okay, and this way you can eliminate the effect of hysteresis, but that's an important effect in any magnetic material. Okay, any questions here? No? All right. Sounds good. So let's do some exercises then, if there are no questions. Let's start with this one. We have a magnetic core in this actuator that has an air gap between the plate and the core. This is made of cast steel with a magnetic permeability of 1.5 times 10 to the power of -3 Henry meters to the power of -1. So this is the absolute permeability, right? It's not the relative permeability. The coil has 250 turns and the coil resistance is 5 ohms. For a fixed air gap of 5 millimeters, a DC supply is connected to the coil to produce a flux density of 1 Tesla in the air gap. Calculate the required DC voltage and calculate the stored field energy. Here we have 1 Tesla everywhere because apparently the cross section seems to be the same everywhere. This should be 5 centimeters if it's missing. So it gives us the same cross-sectional area everywhere. And the depth is 5 centimeters. Okay, so let's start by calculating the DC voltage to this. How to calculate the DC voltage in this system? Any ideas? How would you start this? We want to establish 1 Tesla there. We apply a voltage here. We have a current flowing through. How do we determine the required voltage?
Do we start by solving for current?
Solve for current, exactly. And how do we solve for current? How do we relate the current through to B here?
We could start with the NI equation.
Exactly. We start with our favorite equation, integral of HDL equals to NI. All right. What is HDL? We have 2 elements here. We have the core and L core plus gap, L gap equals to NI. And we know that we have 1 Tesla here because the cross-section of Tesla means the flux density, that's B, right? That's flux density. And because we have the same cross-section, if you have 1 Tesla here, we should have 1 Tesla everywhere else as the flux density. So how can you relate this to B? What is the relation between H and B from lecture 2?
Is it a B over permeability?
B over permeability. B equals to mu H. B over mu equals to H, which means that here we can have BC mu C LC plus BG mu G LG equals to NI.
I have a question.
Yes.
Shouldn't you multiply the permeability by like the permeability of like 4.07?
Yes, yes. The permeability of this is the absolute permeability. Like mu C is the absolute permeability, which is the relative permeability times mu 0.
Okay.
Okay, but we are given the absolute permeability. The question gives mu as 1.5 times 10 to the power of -3 Henry meters to the power of -1. That is not the relative. Relative that doesn't have a unit. This is the absolute permeability already.
Okay, so that's not required for this question.
That's not required. Yeah.
Okay.
But if I had given you, let's say, relative permeability of 10,000, then it would be 10,000 times 4 pi times 10 to the power of -7.
Okay.
Okay. All right. So we have 1 Tesla for B. This is the core. The permeability of the core is given as 1.5 times 10 to the power of -3. What is the length of the core? What is the length of the magnetic core? Any ideas? We can start in the middle here to the middle point there, right? So from here to here, what is this distance?
15.
15. So that's 15. All right, this is 15, which means that this is also 15. All right, so you have 2 times 15, and then you have this distance here, of course, without that portion. What is the distance there? Sorry, this should be in the middle. A bit misleading here. It should be right in the middle there. What is that distance?
Also 15.
It's also 15. So if this is also 15, then the top here is 15. So I have 4 times 15. Is that clear? 4 times 15 centimeters, so times 10 to the power of -2. Yeah. Plus B in the air gap is also 1 Tesla divided by the permeability of the air gap. That's 4 pi times 10 to the power of -7. That's air. And what is the length of the core path? What is the length of the core path? Sorry, what is the length of the air gap? The air gap. Core path we just
10.
calculated, that's that. What is that for the air gap?
10.
10 millimeters, right? 2 times G. We go here and we loop around, right? So we pass through the air gap 2 times. That is 2 times 5 times 10 to the power of -3. Right, this is given in millimeters. And this is equal to 250 times I. 250 is the number of coil turns. And this gives I, if you solve for this, as 33.43 amps. What is the voltage required to establish 1 Tesla now? Well, we know that the coil has a resistance of 5 ohms. So the voltage is simply I times R, which is 33.43 times 5, and that is 167 volts. Okay. Any questions here? No? All right. So if there are no questions, we can move to the second part of this question, and that is calculate the stored field energy. There is a R missing there. Now let's calculate the stored energy in the magnetic field. Let me just erase the light board quickly, and then we'll do that one. And to do that, we can start by thinking about the volumes. We need the volume of the magnetic core, and you need the volume of the air gap. So think about the volume. Here we need to consider now the depth to calculate the volume. So as I erase here, we start thinking about how to determine the volume for both parts. Okay, I'll just leave that now because it's a bit harder to erase. Okay, let's calculate now the star energy. We saw that the star field energy depends on the volume of the air gap and the volume of the magnetic material. What is the volume? To calculate the volume here, we can define two volumes. We can take this part here first and calculate its volume like that. And let's call this volume V, how did they call it? V1. Now we have a depth here of 10 centimeters. We have 5 centimeters like that, and you have the height here is 20 centimeters. So you have this volume V1, which corresponds to this volume here. Is the same, right? We see the same dimensions. So we can trace something like that. Right? And this is also volume V1. This is a bit misleading here. Let's go down like that. This is also volume V1. Is this clear? Yeah? Okay. And if that is volume V1, then you can define now a second volume here, which is that part. This part here and here, we can call this volume V2. If that is volume V2, then there's also volume V2 here. So our total volume is 2V1 plus 2V2. Questions?
I could have also approached it where I take the volume of a big square minus the volume of a square hole.
Oh yeah, there are many different ways to do this. Yeah, this is just one, for sure. All right, so let's look at the volume V1. How do we define volume V1? Volume V1 is 2 times volume V1. We have the depth, which is 0.1, 10 centimeters. What else? We have the height. What is the height? There is 20 centimeters. Now we are not considering the mean car path was from here to here. Now we are considering the entire volume. So it's 5 plus 10 plus 5. So that is 0.2. And we also have the width here, which is another 5 centimeters. So that's times 0.05. This 2 comes from the fact that we have one volume V1 here and one volume V1 there. Okay, plus 2 times. Now tell me what V2 is. What is volume V2?
Is it 10 times 10 times 5?
10 times 10 times 5 millimeters. Yes. Yes.
Oh, is it in
precisely.
centimeters?
Sorry, centimeters. Yes, you're right. Yeah. So that's 10 for the depth. Right, 10 for, sorry, here 10 for the depth, times 10 for the width, and times 5 for the height. So 0.1 times 0.1 times 0.05. So this gives a total volume. This is for the core as 0.003 cubic meters. Okay. We are looking at the energy stored in the core only, so we don't need to worry about the air gap. Any questions here? Or are we good? Yeah. All right, now that we have the volume, we can calculate the energy density. And when you calculate the energy density and multiply that with the volume, we have the energy. How did we define the energy density in the core? The energy density was integral of H dB. The energy density in the core. If you look, let's say we plot the curve HB here. BH. this is if you're operating in a linear fashion, it should go like that. When you reach 1 Tesla, what is this value here? What is H? When you reach 1 Tesla, what is H?
Is it 1 as well?
It is 1 over the permeability, right? Remember that the relation between them is this, right? So, sorry, this is H. All right, so H equals to B over mu. B is 1, and mu was given. So this point here would be 1 over the permeability of the core, which is 1.5 times 10 to the power of -3. Does this make sense? Now, when you are at 1 Tesla, we are at 1 over 1.5 times 10 to the power of -3. This down here is the permeability, and 1 is that. So B over mu. Right? And what is this integral? What is this integral? Well, it's this area. How to calculate that area?
Just do
This
half base height.
Yeah, this times that. B times H divided by 2. All right, so that would be 1 times 1 over 1.5 times 10 to the power of -3, all divided by 2, and this is 333.3 joule cubic meter. All right, but this is an approach for kids. Let's do the integration here. Now, why do things in an easy way if you can complicate them? So this is 1, 0 to 1. Integral of H is B over mu dB, which is B squared over 2 mu, which is the same we had here, right? B is B times H here is B times B over mu, B squared over 2 mu. That. All right, and this gives the same result. So we have B squared is 1 squared divided by 2 times the permeability, 1.5 times 10 to the power of -3, which is the same 333.33 joule meter to the power of 3. This is the density. You see the per cubic meter. What is the actual energy stored in the core? The energy stored in the core is the energy density times the volume of the core. So just multiply this and that volume. And this is equal to 1 joule. Okay.
I have a question.
Yes.
How come we don't consider the magnetic field energy from the core?
In the air gap, you mean?
Yeah, sorry, in the air gap.
Yeah, well, the question only asks for the core. Right? This is only the core. The air gap will have its own energy.
I thought it just said calculate the stored field energy. I don't see where it specifies for the core only.
All right, well, let's calculate that then. Let's calculate that. You're right, actually. Calculate the stored field energy. So this is the core energy, 1 joule. All right, so let me make some room here, and let's calculate the other one. The other one is relatively easy as well. So you can go ahead and calculate the volume of the core. What is the volume? Sorry, the volume of the air gap. Calculate the volume of the air gap. All right, so what is the volume in the air gap?
Point 0.0005.
0.0005. Yes, how did you calculate that?
It would be 10, which is the depth.
So
Or
2
you could
times
do-
this
right,
volume,
2
right?
times that
So,
volume, exactly.
so 10, 0.1 times so that's the depth times
The 5 millimeters, so
5 millimeters.
Yeah.
Millimeters, right? 10 to the power of -3.
correct. And
And
then times 5 again. No, times 10 again.
times
Or
this, yeah.
oh, you did
Yeah,
2
times 5 because of 2,
right?
right? So times
Gotcha.
0.05. And this is 0.005, sorry, 0.05. 0.05 times 10 to the power of -3.
Yes.
I remember that this is given, it needs to be given in millimeters, in meters. So now you can calculate the energy density in the air gap as B squared over 2 mu 0. Mu 0 is the integration that we did before now, but for a mu 0 in the air gap, that is 1.2, 1 over 2 times 1 squared divided by 4 pi times 10 to the power of -7. And this is 397 times 10 to the 3 joule per cubic meter. And what is the energy in the air gap now? Is the volume times that. When you multiply them, we get 19.85 joules. That's the energy is stored in the air gap. Now notice something interesting here. What was the energy stored in the core? 1 joule. The energy in the air gap is 19.85 joules. A lot more energy is stored in the core, in the air gap, than it is in the core. Why is that?
The permeability.
Why is that? The permeability, exactly. It takes much more energy to magnetize the air than it takes to magnetize the core, because the permeability of the core is much greater than the air. All right, any questions?
Yeah, sorry. Just with a notation. What is that symbol? Is it lowercase w and then capital W for energy?
Yes, this is W case W, lowercase, and this is uppercase.
Okay, thanks.
Okay, any questions? No? Okay, if there are no questions, then we can do one more exercise. I'll let you think about it as I erase the whiteboard. Exercise 39, the relation between the magnetic flux linkage and the current of an electromagnet is given by that relation. We'll see how to determine that relation later. But for now, let's take that relation. And based on that relation that is valid between this limits, for a current of 3 amps in the and the air gap length of 5 centimeters, find the mechanical force in the moving part using the energy and the co-energy fields. All right, so we are given the relation between the flux linkage and the current. G is the air gap in the actuator, the same actuator we have been working with. Now we are interested for 3 amps. What is the mechanical force? And we're going to do that using the energy and the co-energy. So let me clean the whiteboard, and I'll do that right away. So in the meantime, you can think about how you would solve this question. Okay, one more second. And we're almost ready to go. All right. All right, so for this question, we have the relation given by I equals to lambda over 0.09, G all squared. G is the air gap. These are constants. Lambda is the flux linkage. We want to calculate the force acting on the actuator. You notice that this is only valid for a certain range of current and air gap, which means that after a certain value, the system becomes saturated and this relation doesn't hold anymore. We are at 3 amps, so we are within the range specified for the validity of this equation, so we can proceed. So let's now do that using the energy. We want to calculate the force when the air gap is 5 centimeters and when the current is 3 amps. So let's start with perhaps the energy. Using energy. What is the definition for this? Is the integral from 0 to lambda of I d lambda. This gives integral from 0 to lambda. I is given there. Integral of lambda over 0.09 times g squared d lambda. This integral is easy to calculate. What is the result there? We have g squared over 0.09 squared times the integral of lambda squared d lambda, and that is lambda squared over 3. Lambda squared over 3. Right? From 0 to lambda gives that. What is the mechanical force? The mechanical force is the derivative of the field energy with respect to whatever is moving. What is moving here is the air gap. The air gap is decreasing. That's what is creating the change in the magnetic field. That is what creates mechanical force. So dg, dwf dg. What is that relation? What is the derivative of this with respect to g? It's 2g divided by 0.09 lambda to the power of 3 over 3. This is the mechanical force. Okay. Any questions here?
Yeah, could you go over that equation again?
Which one?
The mechanical force one.
The mechanical force is the derivative of the field energy with respect to whatever moves in the mechanical system. And if you take this example here, this is moving. The only thing that is changing in the core is G. G is changing. So if you take the field energy, take the derivative of that with respect to the moving variable, which is G. We called that X before, it's G now, is the air gap. Then that gives the force developed in the system.
Shouldn't the, sorry, go ahead.
I was going to
Yeah.
say the same thing. Denominator would be 0.09 squared, I believe.
Yes, squared. All right, so 2g is the derivative of g squared, is 2g. All right, so how we get the current? Well, the current you can get it, or lambda we can get from here. If you isolate for the current, we know the current. So we can rewrite this expression as lambda equals to square root of I times 0.09 divided by g squared. By g, sorry, just g. Right, but just to rearrange this equation, take the square root of both sides. That's the square root of I. That multiplies 0.09 divided that by G. You can see it there. Can you? Divided by G. And that's lambda. So we have the current, we have G. For 3 amps and for 5 centimeters, this gives 3.11. What is the unit for the flux linkage? It's the unit for the flux, which is Weber times turns. Weber turns. And with this, we can now replace everything in here. We have omega, we have lambda, we have G. We have 2 times 5 times 10 to the power of -2 divided by 0.09 squared times lambda 3.11 to the power of 3 divided by 3. And this is 124 newtons. That's the force deployed in the mechanical part. Questions? No? No questions? All right, if there are no questions, then you can do the same, but now using the co-energy. What is the equation for co-energy? That's integral now from 0 to I of lambda di. Okay. So the current is given here. We can get lambda by isolating lambda from this equation. That is the same we got down there. So this would be equivalent to the integral from 0 to I of lambda, which is square root of I times 0.09 divided by G di. All right, but just to rearrange in this equation, again, take square root of both sides and then rearrange for lambda. Replacing lambda here, that's what we get. If you take that integration now, what is the result? Is 0.09 over G times the integral of square root of I di. What is that? What is the integral of square root of I?
Is it 2 over 3 times I to the power of 3 over 2?
Exactly. Here we have it. We have I. Right? We have pretty much everything. Now let's calculate the mechanical force. The mechanical force is the derivative of the co-energy with respect to G. We can put a negative sign here to avoid confusion. We're going to get a negative sign otherwise, or just leave it and neglect the negative sign later. The derivative of field energy with respect to G. What is this result here? What is the derivative of this expression with respect to G? It's negative 0.09 times G divided by G squared, 2/3 I to the power of 3/2. Right? G goes upstairs, G to the power -1. I take the integral of that. There we are. Take the derivative of that, not the integral. Okay, I is 3 amps. G is 5 centimeters. If we replace everything here, we find the mechanical force as negative 124 newtons, which is the same we found before here, but now with this negative sign. For the purpose of our study here, we can neglect the negative sign, right? So to avoid that negative sign, when you calculate the force, we can always add this negative sign here in the definition of the co-energy. It doesn't really change much if you're only interested in the magnitude. Okay. Any questions?
For an exam or a midterm, how complicated would these integrals get?
Complicated will be too.
Like these integrals are fairly simple right now, but would they get more complicated on an exam or a midterm?
No, there's no need for that.
Okay.
Even though you're expected to solve whatever integral is given to you now in 30 year, right? But we are not going to go that far. To be completely honest, this is not going to be used much in practice because this is too easy. The equation here was given already. The actual question is how to get this equation. The derivation here and integration, that's easy. But the true question in the modeling problem is, where is this coming from? Where is this relation between I and lambda coming from? And that's what we're going to see in the next 1 or 2 lectures.